Environmental Systems and Societies, Pearson book, IB Diploma Programme, Chapter 4. Okay, we're going to read it together. Chapter 4 is called Water. Got a nice picture there of a fjord of some sort. All right, so the guiding question for 4.1 is, how do water systems support life on Earth, and how do they interact with other systems, such as the carbon cycle? What's a carbon cycle? You remember that? Do you know about that? All right, so first off on page 336 is the list of understandings that you need to know. I think I'm going to read them at the end of the chapter. If I read them now, it's just a long list of stuff that you have no context for and don't really understand. So what I'll do is, I'll start with the chapter, and then at the end of the chapter we'll come back and go through this, because then when I read through it, it'll sound like a review or a summary. Speak of summaries, are you taking notes? Do you have a pen and paper? Because success starts today. And what I mean by success, we know we're talking about passing that IB exam, right? You want to pass that exam? We're going to start passing it today by reading this book together. All right, so we're going to start with 4.11, movement of water in the hydrosphere. Hydrosphere, I like that word. That's a nice word. Okay, water can exist in 3 phases within the atmosphere. Okay, yeah, the atmosphere is the envelope of gases surrounding the Earth and everything between that and the crust, right? All that's atmosphere. Okay, so water can exist in 3 phases. It can be solid, which is tiny ice crystals, right? It can be liquid, for example, water droplets, and it can be gas, water vapor, the steam. Like when it's a cold day outside and you exhale and you see that misty stuff, it's water vapor. Okay, or when you're watching a pot boil, water pot boil, all the smoke that comes out, it's not smoke, it's water vapor, right? The hydrological cycle involves several processes. Okay, hydro it just means water. Okay, so hydrological means the water cycle. Why does English do this? It could just say water cycle. Why do we have to call it the hydrological cycle? But anyway, that's how it is. Hydrological cycle. It involves several processes. Okay, so these could be the different components that make up the cycle. Solar radiation coming from the sun, is needed for evaporation and evapotranspiration, which move water from the Earth's surface to the atmosphere. Okay, so you have water on the surface, like in a lake or inside a plant, or, anywhere really. So solar radiation is needed to evaporate it, okay, to make it go from liquid up into vapor, okay, which moves it from the surface up into the atmosphere. Heat is released when water condenses, okay, when water comes out of the air onto a surface, right? So heat is released when water condenses, and you can see that in figure 4.1, condensation on a window. Okay, precipitation moves water from the atmosphere to the Earth's surface due to gravity. So precipitation, that's rain and snow. That's water coming out of the atmosphere out of the vapor form into the liquid form. Air movements, including winds and weather systems, redistribute water from place to place. Okay, so all of these processes are part of the hydrological cycle, the water cycle. Okay. So solar radiation drives the hydrological cycle. Okay, that's the engine here. That's what's making it all go. Take away the sun, you don't have a hydrological cycle anymore. Okay, so changes in temperature can cause changes in moisture from one phase to another. Talking about the water phases, from liquid to vapor, vapor to liquid, and so on, okay? Changes in temperature can cause changes in moisture from one phase to another, as shown in figure 4.2. These changes are liquid to solid by freezing, solid to liquid by melting, liquid to gas by evaporation, gas to liquid by condensation, solid to gas, that's called sublimation. That one you may not know or might need a refresher on, sublimation. Even I had a hard time pronouncing it there. It's not a word you use very often. Sublimation, that's going from solid, so from ice, right, or crystals, snow, to gas, which is the vapor form. That's sublimation. Or gas to solid by deposition. Okay, so coming out of the vapor form into the solid form. And then there's a nice little picture here. You might want to draw this picture, figure 4.2, phase changes of water. Write all the different words. Got the little arrows in there. It's good practice to remember which one is which, especially these more, unusual ones. I mean, condensation, evaporation, sublimation, you might know those, or sublimation you might not know, but condensation, evaporation, you probably know. Freezing and melting maybe also, but sublimation and deposition might be new ones. Okay, and we've got a little fact box here. In systems diagrams of the hydrological cycle, stores are shown as boxes and flows as arrows. See also topic 1, section 1.2.3, figure 1.29. So you can go check that out in the book if you don't remember how system diagrams work, because we're gonna see a bunch of those in this chapter. Okay. Whereas figure 4.3 shows the hydrological cycle as an image. 4.3, it's going ahead, so that's the next page. Oh yeah, on the next page they've got a really nice figure 4.3. The drainage basin hydrological cycle. So that's not a system diagram, it's an image. The book is making a good point about making that distinction. Okay, so section 4.1.2. The global, now we're talking about the whole Earth here. The global hydrological cycle is complex. Several parts of the cycle cannot be observed. Therefore, to enable our understanding of how the cycle works, scientists use a systems model known as the drainage basin hydrological cycle. Okay, and that's figures 4.3 and 4.4. So take a look at those. This is a simplified structuring of reality. So this is not exactly how it is. Reality is more complex than these pictures. Okay, this is a simplified structuring of reality that shows just a few parts of the system. The drainage basin, drainage, think about drain, think about water moving down. The drainage basin is studied rather than the global system, as it is easier to observe and to measure. Okay. The basin, basin is a word that also means like a big bowl is a basin. The basin cycle is an open system. Kind of makes sense that it's called a basin, like a big open bowl. The basin cycle is an open system, and the main input, that's where the water comes in, it's coming into the system, is precipitation. Remember what precipitation is? That's water coming from the sky. It can be snow, ice, like sleet, rain. Okay. Main input is precipitation, which is regulated by various means of storage. That's interesting. What do they mean by that? Let's look at these pictures. Okay. So figure 4.3 is the drainage basin hydrological cycle. It shows the clouds there at the top. That gray rain coming down, showing precipitation. Doesn't have to be rain, can be snow. And the ice freezing there on top of the mountains. Okay. So see how this is like at an incline from the top of the mountains, and then the rivers flow down. It's like flowing down the side of a big bowl. Okay, that's why it's called a basin. Okay, it also shows a little sublimation could happen from the mountaintop back up into the vapor. Advection, that's a new word there. Advection, which means wind-blown movement coming from the side. Well, your ice up there and your snow, it melts, it goes down into the rivers. It can go down into the water table, which is underneath the ground, right? Into a reservoir, which is like a little lake there. You have infiltration. That is, infiltration is the word for water going into the soil or into the dirt, into the sediments. Okay, you've got groundwater flow, so there is water that moves through the sediments, through the dirt. Okay. And so that's not necessarily a river. A river is like a big open water flow, whereas groundwater is like, for example, sometimes it can be quite sandy, like it's a sand layer, and the water is moving through the sand layer. Okay. And then we've got a bit of interception, and we've got, let's see, surface flow there, overland, surface runoff, going down, stream flow down into the ocean. Okay, and then there's a few other arrows showing transpiration, taking water up, back into the atmosphere, condensation, bringing water down onto the trees, and evaporation, changing a liquid to a gas or vapor, going up from the ocean. Okay, and so take a good look at this model. Spend some time with it. Okay. And remember that they said that that is an image. This next picture, figure 4.4, is a systems diagram, okay? So this is the drainage basin hydrological system cycle as a system, okay? With the different boxes and the arrows showing things. It's basically showing the same thing, but showing it as a kind of schematic instead of as a picture, like instead of as an image of land features. Okay. Take a good look at that. Read all the different parts to it. Maybe even copy it into your notes. You know, copying it can help you remember it. And then when you're just studying your notes, you've got the schematic there. There you got the systems diagram. Okay. So the global hydrological cycle operates as a system with stores and flows. Now we're moving on to 4.1.3, stores in the hydrological cycle. Now you know what stores are. Stores are not places where you buy and sell things in this book. Stores mean something else. Stores in the hydrological cycle can be divided into saltwater and freshwater stores. Oceans and seas make up the saltwater stores, whereas freshwater stores include glaciers and ice caps, rivers and lakes. If you're not sure what glaciers and ice caps are, go ahead and take a moment to look them up. Soil water and groundwater in aquifers. Aquifers are permeable rocks that can store water. Okay, that means that water can go into the rock. Okay, the rock has like little holes in it, and the water can go into it. The atmosphere and organisms. Water can be stored in organisms like us. We're large bags of mostly water. Here we have figure 4.5, stores in the global hydrological cycle. Okay, so you can see through these different diagrams how the percentage is divided up. 96.5% salt water, 3.5% fresh water. We don't have a lot of fresh water compared to salt water. And then next to that, you see a little bit more zoomed in on the freshwater bit so that you could see the differences there. That teal color is groundwater at 1.7%. Glaciers and ice caps have 1.7% as well. And then there's some tiny bits here. Surface freshwater, so in lakes and rivers and ponds, 0.02%. The amount that's in the atmosphere, like up in the clouds, is 0.001%. Well, I think fog might count as that also. And inside organisms is 0.0001%. So even though we're mostly water, we're still very little of the water that exists on Earth. Okay. The stored percentage values are approximate. Okay, so these values are obviously approximate. There is no need to memorize them, but you should have some idea of their relative importance. So it's a good idea to know that the water on Earth is mostly salt water. And the fresh water on Earth is mostly groundwater and glaciers and ice caps. Okay, so lakes and rivers is very little bit, very, very little of the total amount of water on Earth. And then we have a table here, table 4.1, size of stores and residence time in the hydrological cycle. Okay, I hope you remember what residence time means. How long the water usually stays there. Okay, it goes through the different stores: oceans, atmosphere, rivers, lakes, inland seas, soil moisture, groundwater, glaciers, and ice caps, and organisms. The estimate of their size, and the estimate of their residence times. It's good to look over that table if you get a chance. Open the book to page 339 and take a moment to look at that table. The oceans hold 96.5% of the water on Earth and are therefore the largest component of the hydrological cycle. And we saw that, didn't we? In that what's it called? That figure. Ocean water is continually moving due to winds and tides, and this movement has a significant impact on climates around the world. Ocean currents are also driven by changes in water density as the denser, colder water sinks and less dense, warmer water rises. According to table 4.1, that was that table that mentions the size of stores and residence time in the hydrological cycle, glaciers and ice sheets are the largest freshwater component of the world's freshwater. Ice currently covers about 10% of the Earth's terrestrial surface. Do you know where it is? Remember the seventh continent? So it's mainly at high altitude, up in the mountains, and high latitude, the poles, right? The Arctic and the Antarctic. Although at the height of glacial advances during the Quaternary Ice Age, well, that was a long time ago, they covered about 30% of the terrestrial surface. So when they say terrestrial surface, they just mean Earth's surface. But they decided to be fancy and say terrestrial. Groundwater is the next most important freshwater store. Much groundwater lies deep beneath the surface at a depth of more than 600 meters. That's deep. But some is closer to the surface and can be used by people and plants. Some groundwater is tens of thousands of years old, such as the groundwater beneath the Sahara and Arabian deserts, and so it's essentially a non-renewable resource. Rivers and lakes are the most accessible forms of fresh water to humans, although several sources are highly polluted, unfortunately. 4.1.4 flows in the hydrological cycle. All right, table 4.2. Let's look at this table. Annual exchange, thousands of kilometers cubed. Let's read the text. The hydrological cycle includes evaporation from oceans, water vapor, condensation, precipitation, runoff, that means water running along the surface of the ground from the rain, groundwater, and evapotranspiration. All of these are listed in this table. 77% falls over the ocean. Oh, sorry, missed a bit here. If 100 units represent global precipitation, on average 860 millimeters per year, 77% falls over the oceans and 23% falls on land. Okay, so that's the snow and the rain and whatnot that falls out of the sky. 77% is over the oceans. About 84% enters the atmosphere by evaporation via the oceans. So that's where most of the clouds come from. They come from evaporation of the oceans. Thus, there is a horizontal transfer of 7% from the land to the sea. Of precipitation over the land, 16% is evaporated or transpired, and 7% runs off to the oceans. There may be some time lag between precipitation and eventual runoff. About 96.5% of all free water on Earth is stored in the oceans. Now, we saw that on the other page, right? 96.5% of the water is in the ocean. Precipitation. Ooh, this is a bolded word. You should be sure to write this down. Precipitation is the conversion and transfer of moisture in the atmosphere to the land and includes all forms of rainfall, snowfall, frost, hail, and dew. Okay, if those are new words for you, take the time to look them up. Always good to build your vocabulary, especially if English isn't your first language. Interception, bolded word, write it down, refers to the water that is caught and stored by vegetation. That means mostly plants. Water not stored by plants may be lost through. Okay, now we're going to have some points here. Interception loss, where the water is retained by plant surfaces and is later evaporated away. Through fall, where the water either falls through gaps in the vegetation or drops from leaves, twigs, or stems. And stem flow, where the water trickles along twig and branches and finally down the main trunk. So this is water that falls onto the plants, but runs away in different ways, right? So either it like sits on the leaf and then evaporates, or it kind of falls down through the leaves and hits the ground, or it runs along the side of the plant and goes down into the ground. So this is water caught and stored. Evaporation, bolded word, write it down, is the process by which a liquid is changed into a gas. It is the conversion of liquid precipitation to water vapor in the atmosphere. It is most important when it happens to the water from oceans and seas. Remember, that's where we get most of our clouds from. Factors affecting evaporation include meteorological factors, it's weather factors, such as temperature, humidity, and wind speed. Temperature is how warm and cold it is. Humidity is the amount of moisture in the air, right? Already in the air. And wind speed, how fast the wind is blowing. Of these, temperature is the most important factor. Evaporation increases under warm, dry, and windy conditions. Evaporation decreases under cold, calm conditions. Other factors include the amount of water available, vegetation cover, so the amount of plants, moss and stuff like that you got covering things, and color of the surface. The color of the surface, that matters. Albedo, could maybe also be pronounced albedo, or reflectivity of the surface. So albedo just means reflectivity. So how likely a surface is to reflect sunlight. For example, lighter colored surfaces, such as ice, are more reflective than darker surfaces, such as bare soil. Evaporation losses will be greater in arid, it's dry, and semi-arid climates than they will be in polar regions, like the Arctic and Antarctic. Transpiration, bolded term, is the process by which water vapor escapes from living plants and enters the atmosphere. The combined effects of evaporation and transpiration are normally referred to as evapotranspiration. Evapotranspiration represents the most important aspect of water loss, accounting for the loss of nearly 100% of the annual precipitation in arid areas, dry areas, and 75% in humid areas. Purely evaporative losses only occur over ice and snow fields, bare rock surfaces, desert areas, water surfaces, and bare soil. Infiltration, bolded term, is the process by which water soaks into or is absorbed by the soil. The infiltration capacity is the maximum rate at which rain can be absorbed by a soil in a given condition. So, soil of a certain status. Infiltration capacity decreases with time during a period of rainfall until a more or less constant value is reached. Infiltration is inversely, if you don't remember what inversely means, you can look that up. Infiltration is inversely related to overland runoff and is influenced by a variety of factors such as duration of rainfall, antecedent, which means pre-existing, levels of soil moisture, soil porosity, vegetation cover, raindrop size, and slope angle. In contrast, overland flow, which is surface runoff, is water that flows over the land surface. It occurs when precipitation exceeds the infiltration rate. Okay, so when you got more rainfall than what can be soaked up into the soil, and when the soil is saturated, all the pore spaces are filled with water. Okay, so because soil is not it's not a rock, right? It's not solid. You know, there's space between the bits of soil, so water can go in. But if the soil is saturated, well, then it's completely clogged up. In areas of high precipitation intensity, so really intense rainfall, and low infiltration capacity, soil that can't suck up much of it, can't take it, overland runoff is common. Okay, so it just keeps going. So the water just runs along the surface instead of going into the dirt. This is clearly seen in semi-arid areas and in cultivated fields, things like farmer fields. By contrast, where precipitation intensity is low, just sprinkle, 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 and infiltration is high, most overland flow occurs close to streams and river channels. Condensation, bolded word, is the process by which vapor passes into a liquid form. It occurs when air is cooled to its dew point or becomes saturated by evaporation into it. Further cooling leads to condensation on surfaces to form water droplets or frost. That's why your ice cold can of soda gets all wet on the outside if it's a hot summer day. Sublimation, bolded word, refers to the conversion of a solid into a vapor with no intermediate liquid state. So going from solid to vapor. Under conditions of low humidity, snow can be evaporated directly into water vapor without entering the liquid state. Did you know that snow can just evaporate directly? The reverse of sublimation, deposition, that's also bolded, occurs when water vapor changes directly into ice, such as snowflakes and frost. Advection, bolded word, advection, is the movement of air and water in a horizontal direction. It's not down from the sky like this, such as the transfer of heat and water vapor from low latitudes to high latitudes. Percolation refers to the downward vertical movement of water within a soil into the underlying rocks. So it's going to percolate through. A long time ago, brewing machines were called percolators. They're still called percolators in some places because the hot water, percolates through the coffee grounds and comes out the other side as coffee. Okay, so percolation refers to the downward vertical movement of water within a soil into the underlying rocks. In contrast, the transfer of water within rocks is known as groundwater flow. Okay, so percolation is when the water goes down through the soil into the rocks or the sediments, and then once the water's down in the sediments, then when they're flowing that way, that's when we got groundwater flow. Rocks that contain stores of water are called aquifers. 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 That's also a bolded word, aquifer. A rock that stores water. Stream flow, bolded word, refers to the runoff or surface water in a defined channel rather than flood flow, where the water spreads out over a wide area. Okay, like a river channel, that groove in the earth that the river or stream runs through.